familiar. I know that you don't know what logs are yet, but all it is another way of expressing an exponent. So this is on 117 in your notes. You're just evaluating these, kind of like mental math. So this is really asking you 5 raised to what power gives you 125, right? So number one, the answer is just 3. So you're really just filling in. Do you have these in a binder, Sean? You can just clip them in, right? So that way they stay in order. Yep. So what about number 2? So 2 is asking you 2 to what power gives you 1/8. So how would you flip it over? What? All right, so it's -3 because 2 cubed is 8, and then the -3 would flip it over. Let's do 2 more together. So number 3, how would I go from 36, so 36 to what power gives me 6? We're on 117, Ethan. 36 to what power would get me down to 6? So we've used a positive exponent, we've used a negative exponent. How about a fractional exponent? The 1/2 power, because that's really the square root of 36, which gives you 6. The last one I want to do before you try some on your own is number 6. So it says up here in the directions, when no base is given, use 10 as the base. So number 6 just has a base of 10. So 10 to what power is 100? Great. So the answer to number 6 is just 2. So I'd like you to take 2 minutes and what you got. So 4 cubed is 64. This one's tough. You got to take 27 down to a power of 3. So that'd be the 1/3 power. And then you're squaring it to get 9. So I think 5 is the most challenging one on the whole paper because it's that fractional exponent rule of 2/3. We already said 6 was 2, right? 3 to the first is 3. 5 squared is 25. And 8 squared is 64. Maybe I'll circle these. Good on that row? And then 2 to the 4th power is 16. 11 to the negative first power flips it over. And 3 to the 4th is 81. Sound good? 2 to the 7th is 128. You can always count powers of 2 on your fingers. So you don't need a calculator for powers of 2. Right? 2 times 2 is 4, 8, 16, 32, 64, 128. So 7. Sorry, 14 was a repeat. 15 would be 1/2, right? It's the square root of 25 gets you down to 5. So the base of the log is the base of the exponential expression. This would be -2, 0, and -2 again, right? So what is a logarithm? So a log function, is this big enough? So I made a couple typos when I converted this to a Google Doc. So this should say x cannot equal 0, and this should say a cannot equal 0. I don't know why the time symbol got translated to Google Docs, but x can't be 0. It's going to be part of the domain of our log function. And then a, the base of a log, is never going to be 1 because 1 to any power is 1. So it kind of doesn't work in the log base. And then a cannot be 0. So you can never have a base of 0 for a log. So the definition of a log is just defining it using an exponential expression that a to the y power equals x. To me, this is very abstract. And so I like writing like 2 cubed equals 8 because I know what that means as an exponent. I just like rewriting that log to base 2 of 8 equals 3. So instead of using x's and y's and a's, I just like, it's more concrete for me if I write them using numbers. And you can see that the base here of the exponent is the base here of the log. And I think of it kind of as this circular relationship. 2 cubed gives me 8. So 2 cubed gives me 8. So log functions are the inverse of exponential functions and vice versa. So just like you have addition and subtraction and multiplication with division, square root with x squared. Exponent up until this point doesn't have an inverse relationship, so log is that inverse relationship. So a logarithm is really just another way of writing an exponent. So logs and exponents go hand in hand. And then here's an example again, just that log base 2 of 16 equaling 4 means that 2 to the 4th equals 16, right? So you have to be really fluent with going back and forth between a log expression and an exponential expression so that we can use it to solve when we don't know something. So there's a lot of applications, but we know that 2 cubed is 8. We know that 2 to the 4th is 16. How am I ever going to get 12? So 2 to what power gives me 12? So we don't know how to solve that yet. It's something 3 point something. What is it, 3.5, 3.6, 3.7? So we need a way to solve this function. And all the other functions that we know how to solve algebraically, we do something to both sides of the equation, like subtract 3 to both sides. What are you going to do to both sides? You're not dividing by 2, you're taking the log of both sides. Right, we're logging them. So we're not doing that yet. This is just kind of giving you an introduction to what a log function is. All right, so why don't you try 1 through 4 again? So using exponential form, you should be able to evaluate 1, 2, 3, and 4. So you're telling yourself like 2 to what power is 64? Okay. So you should be able to evaluate 1, 2, 3, and 4. And then 5, 6, and 7, they just want you to rewrite in log form. So for example, for number 5, log base 4 of 16 equals 2. So if you could try 1 through 7, evaluating the top and then rewriting in log form. And if you're confused, so this one, if there's 4 zeros, that must be the negative 4th power, right? 3 cubed is 27. We already did that one. 4 to the 0 is 1. So I just want you to be really careful when you're writing as a log. The base of 2 is the base of the log. That should be a little number, like a subscript. And then the number 1/2 is a full-size number and negative 1 is a full-size number. So there's no exponent when you write a log. There is a superscript up here. There's a subscript down here. So this should all look like full-size numbers. So log base 2 of 1/2 equals negative 1. And then the last one would be log base 3 of 81 equals 4. So it seems pointless right now to change them back and forth. But when we're solving them or putting them into inverse form, you need to be able to go back and forth between these two forms like pretty fluently. So there are 2 different log keys on your calculator. If you've never seen them before, there is a log key and a natural log key on the left-hand side of your calculator. So there's 2 different log keys. The common log is just written log. It has a base of 10, like we already talked about. Just like a square root, you're taking the second root of a number. The natural log, this is actually an LN for natural log. It's on the left side of your calculator next to the 7 and the 4. Yeah, but it's an L. It's a lowercase l, just like this is a log, natural log. It's on the left side of your calculator next to the 7 and the 4. It has a base of E. So remember, E is just a number, right? 2.7. So E is just a constant. And we're going to be using that base when we solve interest problems, population growth problems, because E helps represent that continuous growth that we saw. So E is just a number. So you're just going to use your calculator, type the log of 8, round to 2 decimal places. So if you're doing it correctly, you should get 0.90. Right? You're just typing log 8. So 0.90. So do 9, 10, and 11, and then we're going to talk a little bit about the change of base formula. It does come out negative. You do log of 0.2. Everyone found those buttons okay? Just because when we solve things, it should just be second nature. It's just an operation on your calculator. So I can put up what I got, and then you can just check that you got those 4 answers. And just note that natural log and log are different, right? Because we know that if we had done the log of 100, we would have gotten exactly 2, right? The natural log of 100 is different. It comes out to be 4.61. If the base is different, you get a different answer. So sometimes you can evaluate in your head. The natural log is really, so this is log base 10 of 100. A natural log is log base e of that number. So e to what power gives me 100? 2.718 raised to the 4.61 power gives me 100. That's all e is. It's just a different base. So when you get that, so wait, so what if I want to do like log 3? Yes, so we're getting to that. So if you compare when I grew up to when my parents grew up to when you grew up, the technology available. So my parents were in high school in the 60s. They graduated in 70. So they had tables in their textbook. If they wanted to do the log of 7, they had to look it up in a table of values because the calculators didn't have logs. So then when I grew up in high school, I had TI-83s. So they had the log and the natural log button, but you couldn't change the base. So like what Cole was just saying, how would I do the log if the base is 3? When I was in high school, I used this change of base formula, which allows you to take the log of one number and divide by the log of another number. So in number 12, all you would have to do is take the common log of 8 and divide by the common log of 4, and that changes the base for you. So if we try the log of 8 divided by the log of 4, we should get 1.5 if you type it in correctly. Can you check that you get that on your calculator? You do need to close the parentheses. Okay, so there is a fancy key on your TI-84 calculators. You don't need it if you're at home because you have this change of base formula, but it's under math. And if you go all the way bottom at A, it says log base. I got 1.5 exactly. I did the log of 8 divided by the log of 4. So does everyone see where under math, you've got log base? You could change the base yourself on your more sophisticated calculators. It's under math. The math key, you mean? Yeah, there's a lot under there. We're going to use that in our sequence and series unit too. So math, and you go all the way down to the bottom to number 8, or A, letter A, and it says math base. So you guys have gone from, think about in 50 years where the technology has gone from not having the button at all on the calculator, having to compute it by dividing the 2 logs. Now you can just change the base to whatever you want. So they're pretty powerful. So why don't you try 13, evaluate your math. You could either do math log base or do the change of base formula. What'd you get? 0.63, yeah. Everyone got that one way or the other, right? So pick a strategy. You just need to be able to evaluate logs. Okay. So we've gone from evaluating them mental math to evaluating them with a calculator to now we're going to find inverse functions and also graph them. So those are the other 2 pieces of this. This is the basics of a log function, and then we're going to practice it a bunch and do applications with it to make it more relevant. But this is kind of the skills before the relevance. Okay, so this is going to reinforce inverses though, but you had inverses on your quiz today, so you already know how to find an inverse. What do I do when I find an inverse of a function? What's the first step that you did? Just switch x and y, right? So algebraically, I'm going to switch x and y. So I get x equals 6 to the y power. So I've got y stuck in the exponent. If you're finding an inverse and you're in exponential form, all you need to do is change it into log form because exponents and logs are inverses of each other. So here's where that you're going to be fluent between the two versions. If the base is 6, the base of the log is also going to be 6. And basically the x and the y are changing roles. So y is in the exponent here. That puts x inside the log. So would you agree that these are equivalent? 6 raised to the y power equals x. 6, and if you want to put it in function form, it'd probably be better to write it y equals log base 6 of x. So if you start with an exponential function, you're going to end with a log function and vice versa. Yeah, we are going to put them all into log functions. I'm going to do them with you actually, because I think it's a little bit harder once you get trying it on your own. There's a guided practice we're going to do next class that helps you practice this. Okay, so your first step is to switch x and y. So I've got x equals 4 to the y power plus 1. I'm starting in exponent world. Before I can turn it into log form, I have to get the exponent piece by itself. So I'd have to subtract this 1 to the other side before I change form. So x minus 1 equals 4 raised to the y power. Now I'm going to change from exponent form into log form. So the base of the exponent becomes the base of the log function. X minus 1 would be the stuff inside the log, and then equals y. So if you want to rewrite it as y equals, you can, but as long as you have y by itself, you've solved for a function, y equals log base 4 of x minus 1. If you think about transformation rules, this original function was what? Up 1. The inverse function has been shifted where? Right 1, right? Inside the function. I know we don't know our function, what it looks like yet, but we should be able to read a transformation rule, right? Right 1. So up 1, the opposite or inverse of that is actually to the right by 1. So we're going to see that in a minute when we graph them. You want to try 16 on your own? Why don't you try 16 and we'll check our answer in just a minute. So at least you've tried it first. X and y first. Okay. Is the exponent piece by itself? Yes, it is. So I don't have to add something to the other side. I'm just going to change form. Log base 2 of x equals y minus 3. Right? Because 2 raised to the y minus 3 power equals x. So y equals log base 2 of x plus 3 to get the 3 to the other side at the end. Says what? It didn't make sense? Are you good with switching x and y? Okay. So once you're in the switching x and y stage, you want the exponential part to be by itself. See how in number 15 it wasn't by itself, so I had to subtract 1 to the other side? In number 16, this is the exponential piece. It's already by itself. So the base becomes the base of the log, and then the other two parts switch roles because 2 raised to the y minus 3 power equals x. Remember that circular relationship? And that frees up the y. You don't want to put the y inside the log because then it would still be stuck inside the log. So then adding 3 at the end gets y by itself on the other side. I just rewrote it as y equals, right? I really added 3 to this step. Add 3. So my function is y equals log base 2 of x plus 3. So look, this was to the right, right? This exponential function had been shifted right. So they shifted the log function up. So those are inverses of each other. Okay, so in all of these examples, 14, 15, and 16, what did you start with? An exponential function. What did you end with? A log function. So in numbers 17, 18, and 19, what are you starting with? A log function. What are you going to end with? An exponential function, right? So they're inverses of each other. It's the same process in reverse. So on 17, your first step is to switch x and y. And your second step is to put it into exponential form. You can only do that if you have a base. So what is the base for natural log? So you need to write a little e down there because it's really the log base e. Just like in number 18, that's really the log base 10, right? When there's nothing written there. Not here today. Okay, so if I'm going to rewrite this in exponential form, right? My base of my exponent is e raised to the x power equals y plus 3. So at the very end, I need to subtract 3 to the other side. So e to the x and then minus 3 is like a big minus 3, right? It's not in the exponent. So I started with a natural log, and I'm going to end with an exponential expression with base e, because they're inverses of each other. So, and this is, to me, inverses is the hardest for some reason, because it's abstract. Evaluating logs on the front page, I think, is pretty easy for students. And actually solving application problems is more concrete. The inverses, to me, seem abstract. So if this is the hardest part, hopefully it is. I don't know. So x equals the log base 10 of x minus 5 of y minus 5. You need to have the log by itself before you switch form. So see how over here the y plus 3 was in parentheses? That minus 5 is not in the parentheses. So I need to add 5 to the other side first. So I have x plus 5 equals log base 10 of y. So my last step is to change form. So the base is 10. So it's going to be 10 raised to the x plus 5 power equals y, or y equals 10 to the x plus 5. Okay, so try 19 on your own and see if you can get it. It's not actually as bad as it looks. So because exponents and logs undo each other, the answer to number 20 is just 4, but I wanted to show you the why. So if I write equals question mark, right? I'm trying to evaluate what this is equal to. When in doubt, change form. So if you don't know the answer to this exponential problem, try to change form into a log function. So the base would be 10, right? Right? So 10 to this power equals question mark. So question mark goes here and log 4 goes over here, right? 10 raised to this power gives me question mark. So I'm just changing from, this is an exponential expression. What? Sure. If you want to call this x, sure. X, right? So the base is 10. We're raising it to the log of 4 and we're getting x. Do you see what x has to be? Isn't this log base 10 on this side? Log base 10 of 4, log base 10 of x. Doesn't x have to be 4? But kind of the shortcut is just realizing if your base is the same as your log base, it's going to cancel and the answer is 4. Yep, so the answer is 4. If I ask you what the square root of 8 squared is, what would you say? If I ask you what 8 plus 1 minus 1 is, what would you say? Okay, so inverses undo each other. So you're putting a log with a base of 10 in the exponent of a base 10 exponential expression. They end up basically canceling each other out and giving you 4. I was just trying to show you the proof of why it's 4 if you didn't just accept it on inverse properties. You did not accept it. Okay, so look, 2 cubed equals 8 is written log base 2 of 8 equals 3, right? 2 cubed equals 8, right? I put them in the same places. See how the 2 comes down here, so the 10 is down here. Raised to the third power is out here, so log 4 is out here, and then 8 is inside the log, so my x is inside the log. This is exponential form, this is log form of the same expression. It's just abstract because you don't have numbers. Like here, to me, this is very concrete, right? I've got numbers, I can see that they are equal. More abstract, but if you've got a log base 10 of the same thing, don't the two numbers inside have to be equal? Just like if you had 5 to the 8 equals 5 to the x, don't those two things have to be equal? That's it. On number 21, can I write equals question mark this time because there's an x in the problem? All right, how am I going to evaluate what this is? I'm going to change form again, right? If you don't know what to do and you're stuck, the best thing to do is change form and see if exponential form will help you. So 5 to what power will give me 25 to the x? So it's just simplifying the expression. So the actual answer is going to be in terms of x. How can I make those two things equal? 2x. So the answer is 2x because this is 5 squared raised to the x power, right? 25 is just 5 squared. So see how this is 5 to the 2x? So to make them equivalent, this would have to be 2x. Right? These to me, 21 and 20 and 21 are like the most challenging of the questions you'd have to simplify logs on. Tomorrow, our practice, and actually, did I say you had homework tonight? So I think that we should do the homework for tomorrow. I don't think, did I assign another homework tomorrow? Where's your agenda? Because tomorrow I want us to do the guided practice. So let's look at graphs of logarithms. So if our exponential function is y equals 2 to the x, we just learned how to find inverse functions. It would be log base 2 of x is the inverse. So 2 to the x, log base 2 of x are inverses of each other. So one strategy to graph inverses is to make a table of values for the original function and then switch x and y, right? So we should know how to make a table of values for 2 to the x because we just had a quiz on it. So what's 2 to the negative second power? 1/4. 1/2 is the negative first power. 0 is 1. 2 to the first is 2, and then 4, and then 8, right? I'm doing the powers of 2. So let's graph that first. So the exponential function, hopefully we graphed it right on our quiz. There's the exponential function, right? 2 to the x. Uh-oh, I don't think I graphed this part right. 2, 1, 2, 3, 4, 3, 8. That's still wrong. 1, 2, 3, 4, there we go. So 1, 2, 2, 4, 3, 8. This had an asymptote at y equals 0, right? Okay, so it says, how will this table help us graph the inverse? Don't you just have to flip x and y? So if I want to graph the log function, I'm going to graph 1/4, -2. 1/2, -1. 1, 0. 2, 1. 2, 3, 4, 2. 5, 6, 7, and 8, 3. So these red dots are just, I'm flipping the x and y and graphing them. They should be a reflection over the line y equals x, right? So y equals x should be able to be drawn right in between those two. It's not an asymptote, it's just a mirror image line. And the log function has an asymptote at x equals 0 because the original had an asymptote at y equals 0. So the key point for exponential functions is its y-intercept 0, 1. The key point for log functions is its x-intercept 1, 0. Right? So if you change the base, can I move it to the other page? So we just have 3 graphs left and then we're done. So this one just says, hey, let's graph log base 10 by first thinking about 10 to the x. What are the 3 key points on 10 to the x? 0, 1, 1, 10, it's really steep, and then -1, 1/10. So if you have 3 key points on the exponential function, you should be able to find the 3 key points on the log function, right? 1, 0, 10, 1, and 1/10, -1. So the red is my log function. It has an asymptote at x equals 0. This one had an asymptote at y equals 0. See how it's a reflection over the line y equals x? So let's use the red graph to answer these few quick questions about the log graph. Answer the questions about log graph. What's the domain of this red graph? What are the x values? X all has to be greater than 0 this time, right? Oh, you're leaving, right? So you got that note that we'll do the homework due Monday. Range is all real numbers. Your x-intercept. Yep, he's on his way. Is it increasing or decreasing? So as I trace this red curve, I'm going up, right? I'm going up, so it's increasing, right? I'm going to the right, I'm going up. Any asymptotes? Yeah, x equals 0. It's continuous, meaning I can connect these dots, right? There's actually points in between them. It's not just discrete dot, dot, dot. And the inverse function we said was 10 to the x. Let's start with 1 and 2 next time. Those would be a good warm-up to do next time. All right?